Good day, ladies and gents, and welcome to our next video looking at the design of steel structures, where specifically today we're going to be going through a worked example on beam columns. So the design of the member experiencing both axial compressive load and bending. And we're going to be doing this according to SANS 10162 Part 2 and going through all the steps. Now, I've provided a full worked solution to this simply because you'll see how long all the calculations are. But now let's start getting into the question. Here we have the classed example, and the 6-meter column shown below in Figure 1 forms part of a multi-story building. The structure is braced in both directions, which is important. The loads shown at ultimate limit state, and they've been calculated using a second order analysis. A beam at mid-height provides lateral restraint about only the weak axis, but does restrain both flanges. Select a suitable beam size that would be suitable for the configuration shown. Try only one size, but show all steps even if the section fails one of the checks. So we're going to be going through this now. So let's start having a look and making sure we understand the diagram. So there is our column. We have a compressive load in it, Cu, of 600 kilonewtons. We've got a bending moment of 200 kilonewton meters at the top and 100 at the bottom. Straight bending moment diagram, meaning no load is applied from top to bottom because it's a straight line, there's no change in that. And then also same thing, moment about y-axis, there is a moment double curvature from top to bottom. Now in reality, bending about both axes is actually the exception rather than the rule. In most structures you design it for bending about one axis and then you brace it in the other axis, so you'll have a portal frame and the likes. So it is unusual to find biaxial bending, but it does sometimes happen. Well, especially it's the exception, especially in industrial buildings, unless you have unusual structures and unusual loads where you can't put bracing in. So here's our beam though, and we are told that at mid-height there is a beam connected to it, and it prevents movement of the flange, and that it prevents movement of both flanges. So now let's start seeing how we're going to design this, because we first have to run through all the steps and then get to a stage of how it's going to behave and check all the different requirements. Now I've put the full solution here already. So this is these graphs will come from if you work out all the different failure criteria. And what will happen in our structure now? Let's say there is initially zero load on it. And what we do is we progressively increase the moment and increase the compressive load. And I'm just keeping the ratio of that as per the question with 600 kilonewtons and 200 kilonewton meters. And we load it up and load it up and load it up until we find that either when it's fully loaded, it is within all of these criteria, or we'll actually find in this case we just fail. We just fall outside of the lateral torsional buckling failure, the LTB, but it'll pass cross-sectional, it'll pass overall resistance, fail lateral torsional buckle, and pass biaxial. So in actuality, we'll find in the question the beam size we select is incorrect. We need a bigger one, but let's go through that now. But ultimately, any solution that falls more or less in this bottom feasible zone is okay. And these lines are not as simple as they've shown here. They do change as you change the different variables and shapes, bending moment diagrams, etc. But this gives a good understanding of what's happening. But let's start having a look at how this section is going to buckle, because one of the most important things and one of the most difficult things is normally to get our effective lengths. So first, let's see, what about compression buckling? So we now load our column at the top. We have our compression load on it, and then the section buckles. So if we have a look at section AA, so that's looking from the side here, and we want to see now how would it work in compression. Well, we have lateral restraint at the top and at the bottom for the section, so it can't move at the top and the bottom horizontally, but across its entire length it can. So there's nothing preventing movement. So when it buckles, so this is compressive resistance, the entire cross-section can move horizontally all the way from top to bottom. So that's going to be our then buckled shape. But now when it comes to weak axis buckling, so then we're looking from BB, looking from the side, and we see the entire section buckle sideways, it can't move horizontally. Let's do that in another color actually. It can't move horizontally at mid-height. There. So, and it can't move top and bottom, so the section would buckle something like that. So what you will find here is that our KY is 1, and then our LY is 3 meters. 3 meters. But then when it comes to our effective lengths about X, our KX, also 1, because we're not accounting for any fixities at the end. And you'll see now that we are required to use 1 for this case. Our LX is 6 meter, our LY is 3 meters for compression buckling, so when the entire section can move. Now we come to lateral torsional buckling, and just remember, lateral torsional buckling is failure of the compression flange. Very important, is the compression flange able to move? So now, when we apply a load to the section, so here is our moment, and it's going to, for instance, put this flange into compression all the way from top to bottom. And now let's see, where can that buckle out? Well, actually, sorry, I must actually change that a little bit. The bending moment diagram does swap sides, so then it swaps from compression from one side to another. But if we're going to have a look at the buckling of the section, when the flange tries to buckle, it's restrained from moving, it's restrained from moving, and it's restrained from moving. So the buckled shape would look something like that. So our K is 1, we're not accounting for connections. L is 3 meters. So this is for lateral torsional buckling. We don't have any end fixities, any end connections we're told about to influence effective length. So our K is 1. Load appears to be normal, and then our effective length is between points of lateral support to the compression flange of 3 meters. Now, we also need to see what is our torsional length, between where and where can it twist, and same story, our LZ is 3 meters, and then our KZ is 1. Our KZ is always 1 at the moment with our code. So our torsional length is either the top or the bottom length of about 3 meters. But let's have a look then at the deflected shape. As the structure, as it is loaded, let's have a look at the bending moment diagram here. You can see there's maximum bending. Remember, the curvature is proportional to the moment. So we've got maximum curvature. The curvature gradually decreases until there is 0 curvature, and then it curves the other way. So we have double curvature in this section. So when we plot that, our deflected shape, what the path that it will physically follow, will look something like this. This is very exaggerated, but something like this. Maybe it wouldn't even pass the axis, but we do get double curvature, and we have some delta value, and this is our deflection or our deflected shape. A deflected shape, and that deflected shape is going to be important for determining the influence of the P delta effects later on, to make sure that we are accounting for the influence of the force acting at a distance. So the important thing now is we've got all our effective lengths. Now we can move on with our checks. So first we need a beam size, and we're going to run through the calcs. We've got the references on the left, so if you want to go see either from SANS 10162 Part 1, either from the code or the Red Book, the South African Steel Construction Handbook, the references are listed on the left, and then the outputs. So we're going to try a UB406 17860. We have a look in the Red Book, and it looks, give or take, like the bending resistance is more than enough and the compressive resistance is enough. But let's see, maybe by the time we get to the end, if it's going to work out or not. Now, We're using 355 steel, listed all the properties above, and let's continue on. So our section classification, running through very quickly, this is covered in previous videos, which we find it's a in compression class 3 flange, which is good news. Class 4 web, that's not so good news, that might mean extra work. Now classification in bending, class 1 flange, class 1 web. We do need to include now in the section classification our compression term that does influence it, but all the calcs are there. So it's class 1 in bending, which is good, class 4 in compression. So now we need to see, will it experience local buckling? Class 4 means it might, not necessarily. But now let's check whether stresses are low enough such the entire gross section can be used. And so we do that. The stress is as calculated. We've got our compressive load, we get our stress. You can see that stress is actually quite low. It's a 355 steel, and we've got less than 100 MPa stress. It's the web that failed, so it is supported along both edges. Remember, section classification, it is the web buckling, so it is supported along both webs, both sides, top and bottom. So K is 4, we check our limit, and we actually find even though it is class 4, it passes, so we don't need to adjust our cross-sectional area. Our total effective area can be used, and that's good news. So now let's check the capacity for combined bending and compression. So remember, this equation governs everything. We're going to use this 3 times over, but we're going to change the inputs each time. For our cross-sectional check, we're first going to start off with that. Beta is 0.6, that's stipulated. Lambda is 0, so it's a short beam. There is no buckling. So compressive resistance is very easy. Area times stress. Moment of resistance, very easy. It is ZPL times stress with the partial factor. And so we get all our different resistances. We continue on now. So I'm going to go through this quite quickly. You can check all the details afterwards. U1 factor for second order effects between the ends of the node. So just remember the diagram I was showing earlier. Here we have a deflection, delta. We need to make sure, does that make our situation worse or better? Since we have the maximum moments at the end, it's probably not going to be a big deal, because where the P delta effect occurs, somewhere around here, the moment's a lot lower. So it's probably not going to be a big deal. If the maximum moment was also there, then we'd have a problem. If there was a uniform bending moment, it would be a worse effect. So U1 factor for second order effects between nodes. The column will buckle about strong axis over the full length. So strong axis buckling, full length 6 meters, weak axis mid height. So we use the effective lengths, the LX and the LY, as I showed you earlier, because we're looking at when it undergoes buckling, over what length will buckle, and we've determined that already. Now we get our effective lengths. Well, we've already determined our effective lengths. Now we get our behavior and our compressive loads. So let us continue on. The omega 1 factor accounts for deflection that occurs between points of lateral support. Hence, for the use, hence for excess, use the moments over the full length, and YY use moments between the mid, span, and top. Now, why am I saying use moments between mid, span, and top? Because worst case section. Because I effectively have 2 different beam columns I would going to design here. Because for the bending resistance, the bending resistance has a lateral restraint at mid height. So either I can design the top of the section or I can design the bottom of the section. I have 2 different sections for bending resistance. So we've got to say, which is the worst case? Well, the compressive load is the same throughout. The MY is the same top and bottom, the shape and the magnitude. So those aren't going to influence whether I design the upper half or the lower half. However, when it comes to the moment, the upper half has a higher moment and a worse bending moment diagram shape, because it is single curvature. The bottom has a lower moment and double curvature, so its omega 2 of the top is lower and its M is higher, so that therefore its resistance is lower, its force is higher, so the top section will govern. So I'm going to design this top half. And then we know that the bottom half will definitely work out as well. So that's why I've started picking out that. And let us continue. So now double curvature about XX, giving us a kappa of that value. Remember, I'm looking at the top half. Single curvature about YY. And remember, we're using the full length because we're looking at deformations from start to finish, and it can deform over the full height about X and half the height over Y. And when we work that out, we get they both turn out to be 0.4. In fact, we plug in values and we get U1X and U1Y. So this is the influence of the deflected shape on P delta. And yes, as we suspected, the maximum moments at the end, where the maximum deflection is not at the same place as the moment, so its influence is not as bad. Where the buckling and the P delta effect occurs is not at the same place as the maximum moment, so it's not as big a deal. So, however, remember, check 1 is a cross-sectional check, so we are checking worst case stresses. So check at worst position. We need to make sure that at worst position, i.e. ends. So we need to make sure we don't reduce the moment, because the moment's at the end, buckling somewhere in the middle, so we're not going to adjust our U1 values. Now, let us continue our interaction equation. We plug everything in, and great, it all works out fine. Cross-sectional strength is spot on. So now, let's continue on. Compressive resistance, this is governed by maximum slenderness. Biaxial bending present, K is 1. The code says if you've got biaxial bending, K, your effective length is 1 irrespective. You always take K as 1. So now I'm going to work out my slenderness about both axes, both okay, buckling about Y governs, and then now I get my compressive resistance as we have previously determined. You can refer to previous lectures for that. So it's a doubly symmetric section, so I'm only checking buckling about Y or X, and we found that Y governs because of the higher slenderness. Continuing on. So once we have our longer column, remember check A was short beam, short column, check 2 long column, short beam, so it's still a laterally restrained member. We still have the same resistances as previously calculated. Our U1 values are as per A, but not limited to 1 since frame is braced. Braced frame, you don't have to limit it to 1, so we now use the values as calculated. So those are from above. We can then don't have to recalculate them again. We just don't have to limit them to 1 this time. Our beta value, we go through and calculate it and find out it's not less than 0.85, so we set it to 0.85. Plug all the values in the interaction equation and great, it all works out. We are still fine. The combined beam column resistance is more than enough. Lateral torsional buckling. So now, with lateral torsional buckling, remember, this is when the beam buckles sideways and twists. So we're trying to make sure that both the combined axial buckling sideways and the combined bending buckling sideways, or lateral torsional buckling sideways, are not going to cause failure. So we have to determine the minimum of FEY, FEZ, and FEYZ. So it's based on minor axis or lateral torsional buckling, but for a doubly symmetric section, FEYZ equals FEY, FEZ. Refer to the other video where I have proved this. So now we go through and we calculate our torsional stress. We get all our values. It's a doubly symmetric section, so x0 and y0 are 0. And we continue on, find our torsional stress, our lateral stress, FEY, calculated above, and y-axis governs, so it's from above. We can use that value. Bending resistance, now we have to calculate the moment of resistance, our MR. Calculate considering lateral torsional buckling. Upper section of column will govern resistance since moment is higher and single curvature exists. Lateral torsional buckling will occur between the midpoint and top. So our effective length is 3. So we work out our kappa value, negative for single curvature, omega 2 value, which is fine, M primed CR. Remember, M primed CR is what you find in the red book. It excludes omega 2. So first we calculate our elastic buckling MCR, run through all the steps, and just a side note, even if I make a mistake, at least I show all my workings so I can get marks in an exam. So then continue on. So we get our M primed CR, we multiply that by omega 2, and we then have our total MCR value, our total elastic buckling, get our plastic capacity, and then we run through the calcs and we get a moment of resistance, which is less than phi mpx, so we're fine. We've previously calculated our MRY, and remember MRY is not affected by effective length. The minor axis buckling is constant. Doesn't matter how long or how short the beam is, minor axis bending doesn't undergo lateral torsional buckling. Then our U1 values as per A, but since frame is braced, U1x is greater than 1. So we get our U1 values, plug it all in, and oh dear. We plug it all in and the section fails. The section chosen is 1.5% overstressed. At this point in time, you're going to have to make a bit of an engineering decision. Either you would need to go with a larger beam, or if it is known that the load's effective length analyses on conservative results could be accepted. So if you know you've rounded up the loads, you've approximated the length, it's not 6 meters, it's actually 5.8, etc., etc., you could possibly accept it, but if not, if everything's spot on, you would need a bigger beam size. Then, if it was decided the beam is sufficient, you check your biaxial bending, and we find that is fine. So overall behavior, therefore the section is sufficient except for lateral torsional buckling strength. Either a larger beam is required or loads must be refined. So section fails or we need to refine our loading. So that's taken us through then the design of this beam. So we have all our loading, all our effects, and we checked, remember, cross-sectional strength and the other two checks, and then finally the biaxial check, and you'd even do the biaxial check even if you've got uniaxial bending, run through it all and check it passes. Well, I'd already given you the results showing that it fell just outside of the feasible zone, but we saw that to be true with all the calcs, and you can see as shown here the lateral torsional buckling governs, it's quite a bit away, and then the cross-sectional and overall next, and then biaxial much further down. And it would depend on your effective lengths, it would depend on your ratio of your loads, which would govern, and you may sometimes find that biaxial governs, you may sometimes find that cross-sectional governs, although generally less, but any of them could govern, so you check all of them each time. So hopefully that's given you an overview of doing beam column calcs. Unfortunately, they're quite tedious and very long, so get used to using pre-calculated resources if you can, like the Red Book. It speeds up your calculations a lot, or this is really the sort of thing you want to do in an Excel spreadsheet in reality, because it's way too much effort to do this by hand each time. Okay, hope that's helped, and see you on the next video.